The nth term of a series is given by nx to the power of n, where the modulus or absolute value of x is less than 1. Find an expression for Sn, the sum of the first n terms of the series. Let's look at the first term of this series. The first term is got by replacing n in the general term with 1. If we do that here, nx to the power of n becomes 1x to the power of 1. Let's write down the second term. We replace n in the general term with 2, so we get 2x squared. To get the third term, we replace n with 3. To get the fourth term, we replace n with 4, and so on. We keep going up as far as the nth term, which is nx to the power of n. So I've written down n terms here, and we want to get the sum of those n terms. Now the first thing you could notice here is that this series is not arithmetic. For example, if we take the second term and subtract the first term, we will see that in general it is not equal to, say, any other term. Let's say the fourth term minus the term previous to it, which is 3x cubed. Okay, this is not true in general. Okay, for some values of x, 2x squared minus x will equal 4x to the power of 4 minus 3x cubed, but for most values of x, these two expressions are not equal. As a matter of fact, there are at most 4 distinct solutions to this, because the highest power of this polynomial is 4. But in general, for most values of x, t2 minus t1 is not equal to, say, t4 minus t3. So that proves that the series is not arithmetic. We only have to look at 2 pairs of consecutive terms. Here I looked at the difference between t2 and t1 and the difference between t4 and t3, and in general they're not the same. So that's enough to show that this series is not arithmetic. We don't have to look at other pairs. For a series to be arithmetic, then t2 minus t1 would have to equal t4 minus t3. It would have to equal, say, t9 minus t8 or t10 minus t9. Basically, any term minus the previous term would have to be a constant. So this is the condition for an arithmetic series. If we take any term, tn just stands for a general term, subtract the term previous to it, which is tn minus 1, we have to get some fixed number, some constant that's usually referred to or denoted by the letter d. It's the common difference of an arithmetic series. It is also a fact that this series is not geometric either. Say we take the second term, t2, and divide by the first term. Well, what do we get? We get 2x squared divided by x, which is 2x to the power of 1. Let's suppose we take any other term and divide by the previous term. Let's say t3, and divide by the term previous to t3, which is t2. So that's 3x cubed divided by 2x squared. That's 3 over 2 times x. You can see that 2x is not equal to 3 halves x in general. Unless x is 0. If x is 0, then both of these are the same, but that's only one value of x. 2x is not equal to 3 halves x in general. If the series was geometric, then t2 over t1 would be known as the common ratio. It's denoted by the letter r, and it should be the same regardless of which two consecutive terms I work with, whether it's t2 over t1 or t3 over t2 or t4 over t3, whatever. For a geometric series, the general term tn divided by the term previous to it, tn minus 1, is a constant denoted by the letter r, some number. That doesn't happen here. As a matter of fact, each term in this series can be got by considering the term of an arithmetic series and a term of a geometric series. If we just look at the series 1 plus 2 plus 3 plus 4 plus as far as n, well, we have an arithmetic series. You can see the first term denoted by the letter small a is 1. That's the first term here, t1. The common difference denoted by the letter d is also 1. 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, and so on. So the coefficients in each term follow an arithmetic series. Now if we look at the other part of each term, that's the part involving x, we have x plus x squared plus x cubed plus dot 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 as far as x to the power of n. We see that this is a geometric series. The first term denoted by small a is x, and we have the common ratio denoted by the letter r is actually x as well. If we multiply the common ratio x by any term, we get the next term and so on. So x times x is x squared, x times x squared is x cubed, x times x cubed is x to the power of 4, and so on. So this type of series was not covered on the course so far. So we need to apply a special trick to get an expression for the sum Sn. The trick that we use is to start by multiplying this series by x. So if we multiply x by the first term, we get x times x equals x squared. Now what I will do is I'll write down x squared underneath 2x squared, because we're going to combine these two series. If we multiply x by 2x squared, we get 2x cubed. So again, I'm aligning like terms. When we multiply x by 3x cubed, we get 3x to the power of 4, and so on. Now, what's the second last term in the series Sn? I'll just write it in here. It's got by replacing n in the general term with n minus 1. So we'll have n minus 1 multiplied by x to the power of n minus 1. So this is the n minus first term. So this is tn here. This is tn minus 1. Now we're multiplying this series by x. So what do we get when we multiply x by n minus 1 times x to the power of n minus 1? Well, if we multiply x by x to the power of n minus 1, we just add the powers. So we get x to the power of 1 plus n minus 1, which is n. If we add 1 onto n minus 1, we get n. And of course we have this n minus 1 in front. So when we multiply x by this term here, we get n minus 1 times x to the power of n. So I have to write this term underneath this term here. These are like terms. They involve x to the power of n. So that's the result of multiplying x by the penultimate term of this series. Now we have to multiply x by the last term of this series. X times nx to the power of n. Well, that's just n times x to the power of n plus 1. See, we have x to the power of 1 here, so we add the powers. So the last term in this second series is going to be nx to the power of n plus 1. So now why do we do that? Well, it turns out that we can combine these series in such a way that we get a geometric series. The way we combine them is to actually subtract these series. So we want to take this series here, which is Sn, and subtract this series here, which is x times Sn. So we have 1x minus 0. We can subtract them this way. We can combine all the like terms. It's the same thing as writing this out in a straight line and minusing all this from it on the same line. We will end up with this term here, which is 1x. Then we have 2x squared minus 1x squared. That's plus 1x squared. Then we have 3x cubed minus 2x cubed. That's plus 1x cubed. Then 4x to the 4 minus 3x to the power of 4 is plus 1x to the power of 4. So you can see we're getting a geometric series. So we keep going, and you know, I won't write down what we get when we combine these because I haven't written down the third last term in the second series, but I will combine these two. We have nx to the power of n minus n minus 1 times x to the power of n. That'll actually give us 1x to the power of n. Just to see that more clearly, I'll write it down here. Nx to the power of n minus n minus 1 times x to the power of n. Well, we can just multiply n minus 1 in here, so we get minus n times x to the power of n. Then we have minus minus 1, which is plus 1 x to the power of n. You can see that these cancel out, so we get x to the power of n. Well, we could see that was the pattern all along, so that's no big surprise that we just get 1s here as coefficients in all the terms. Now, this term here is out on its own. There is no term like it in Sn. So we have basically Sn, all of this series, minus all of this series. So we're minusing everything here. including this term. So we get minus nx to the power of n plus 1. Or if you like, we have a 0 out here. So we have 0 minus this term. Gives us this. So now we end up with a series that is mostly geometric, except for this last term. We just string on this single term at the very end. But we can see that all of this here is geometric. What does that mean? It means we get each term by multiplying the previous term by the same quantity. That quantity is called r. So if we multiply x by x, we get x squared. X by x squared gives x cubed. X by x cubed gives x to the power of 4, and so on, all the way up to x to the power of n. The first term is denoted by the letter a. The common ratio is denoted by the letter r. The sum of the first n terms of a geometric series is given by this formula here. Now sometimes you might see the formula written the other way around. You might see it like this. This formula is the same as this formula. You just multiply above and below by minus 1, you get this version. Whichever version you use, it doesn't matter. They're the same. So we have n terms here. See, the first term is x to the power of 1. Then we have x to the power of 2. The nth term is x to the power of n. So there's actually n terms. N terms in this part. So Sn is a, which is x, times 1 minus r, which is x to the power of n. So we have n terms. And we divide by 1 minus x. So by Sn here, I'm referring to this geometric series here. But that's not what we want. We're interested in Sn of this geometric series here. So these Sn's are not the same, of course, don't mix them up. So if we look at the left-hand side here, we have Sn minus x times Sn. Well, we can factorize Sn out of that. So we have Sn times 1 minus x equals, well, we have the sum of this geometric series. It's given by this here. And we just have to add on this term. So Sn times 1 minus x is a geometric series plus this term here. So now at last we can get Sn of the series that we're interested in, this series here, x plus 2x squared plus 3x cubed, etc. We just divide across by 1 minus x. So if we divide this fraction by 1 minus x, what do we get? We get x times 1 minus x to the power of n divided by 1 minus x squared. So we just multiply the denominator by 1 minus x. It's like taking this fraction and multiplying by 1 over 1 minus x. So we get 1 minus x squared in the denominator. And then we divide this by 1 minus x. Now, here I've done a check of this formula for n equals 2 only. Of course, it's true for all values of n. So I just did this as an exercise here. So you just plug 2 in for n. So we get x times 1 minus x squared all over 1 minus x all squared here from this formula, minus plugging 2 in here, we get 2x to the power of 2 plus 1, or 2x cubed over 1 minus x. We can factorize 1 minus x squared as 1 minus x times 1 plus x. That's using the difference of two squares here. 1 squared minus x squared, or a squared minus b squared is a minus b times a plus b. In the denominator we have 1 minus x squared. That's 1 minus x times 1 minus x. So we can cancel one of these 1 minus x's. We can then combine both of these fractions because they both have the same denominator, which is 1 minus x. Multiplying x by 1 plus x gives us x plus x squared, and we subtract this, the numerator of this fraction, which is 2x cubed. So we have them as a single fraction. We can factorize x out of the numerator here. So we have x into minus 2x squared plus x plus 1. We can factorize this quadratic expression into 1 minus x times 2x plus 1. And then you see that the 1 minus x is cancelled here. And we're left with x into 2x plus 1, which is 2x squared plus x. And this is indeed the sum of the first two terms. So it breaks down to this. This is indeed S2. 2x squared plus x, or x plus 2x squared, same thing, sum of the first two terms. So this formula is true for n equals 2, and indeed it's true for all values of n actually. Now before I look at the second part, which is finding the sum to infinity of the series, I want to look at a condition on x. That is, the modulus or absolute value of x is less than 1. What does this mean? it means that x is a number between -1 and +1. So if you ever see something like this, mod x less than a, it means that x lies between -a and +a. Of course, a has to be a positive number. The modulus or absolute value of x is positive, and if it's less than a, clearly a has to be positive. You can check that this makes sense if you pick any number between -1 and +1. Let's say we pick -3/4, and let's get the modulus of it. Well, the modulus of -3/4 is +3/4, and that is indeed less than 1. See, it does obey this inequality. So it's true for any number between -1 and +1. Now, to calculate the sum infinity, denoted by s sub infinity, we have to take the limit as n tends towards infinity of s sub n. So we want to see what happens to this expression as n gets larger and larger, as n tends towards infinity. Well, one thing that happens is that x to the power of n is going to go to 0, because we know that x is a number between -1 and +1. And if we take any number between -1 and +1 and raise it to a power, as the power gets larger and larger, x to the power of n will go to 0. So for example, if x was -3/4 and we put it to the power of n, then as n gets larger and larger, this will go to 0. Okay, if you take any fraction and raise it to a positive power, for example, if n was 2, we would have -3/4 squared, which is 9/16. That's actually smaller than, or that's getting closer to 0. 9/16 is closer to 0 than -3/4 is. That's for n equals 2. If we take n equals 3, then we get a number even smaller than a number that's even closer to 0. So we know what happens to x to the power of n. Now, what's not so obvious is what happens to this here as n tends towards infinity. So we're interested in the limit as n tends towards infinity of nx to the power of n plus 1. We can forget about the denominator here. The denominator doesn't involve n. It's the numerator that we're interested in. Now we could use the fact that the limit of a product is the product of the limits. This is a fact that's not proven here, but we could use it. So we have a product here. So we get the limit as n tends towards infinity of n, which is infinity. If we let n go off to infinity, we get infinity, of course. Now, what happens if we take the limit as n tends towards infinity of x to the power of n plus 1? Well, as you saw earlier, since x is a number between -1 and +1, if we let n tend towards plus infinity, then this will go to 0. So it looks like we end up getting infinity times 0. Now, what is this? Is it 0 or is it, or what is it? It turns out that it's actually 0, even though it doesn't really make sense to write down this product. Okay, so I haven't proven that this is true, but it happens to be true. It happens to be 0. You could use your calculator, say, to check this limit for a specific value of x. Let's say x equals 0.5. X has to be a number between -1 and +1. So let's check it for 0.5. So we replace x with 0.5, and let's just get an approximation to this limit. So let's just plug in a very large number for n. Of course, we're letting n tend towards infinity, but we can pick a large number for n. Let's say we let n equal 10,000. So we have 10,000 multiplied by 0.5 to the power of n plus 1, which is going to be 10,001 in this case. See, we get 2.5 by 10 to the power of -3007. Well, 10 to the power of -3007 is so small it's practically 0. So this is effectively 0. So that was for a value of n, which is 10,000. So you can imagine that for even larger values of n, we'll get an even smaller number. Let's just do one more. Let's suppose n, I'm not going to write this down, let's suppose n is 1 million. So we have 1 million. That's a 1 with 6 zeros. Multiplied by 0.5 to the power of 1,000,001. Okay, it says invalid input here. Actually, that means that there are too many significant figures in the scientific notation. You know, for 10 to the negative value, it could be 10 to minus 7 billion or something, several billion, whatever. That's what's meant by invalid input here. Basically, but actually we will get something even closer to zero. That's what's happening. So what's happening is that this part is going to zero much faster than this part is going to infinity. That must be the case for the overall limit to approach zero. So simplifying this, we see that sum to infinity is x times 1, which is x over 1 minus x squared.